Hey guys, what's up? Welcome back to one of our last days, or one of our last lectures in statistics, Stat 405. Almost done. Hopefully you guys are having a good day, having a good week so far. Just a few left for us. We will be done soon enough. Hang in there. Today we're going to start talking about linear regression. And linear regression, probably the most overstated topic since you start school, whenever that is, and everybody's throwing regression lines around and you're like, what's going on? How do you get all this stuff? And why are you doing a line? And how do you get that? And all that stuff. So I'm going to try to break that down today, really make sense of what's going on with this regression stuff. And then eventually we'll get to hypothesis testing and stuff like that for our parameters for our regression line. So that's where we're going with chapter 12, linear regression, correlation, coefficient, things like that. So we're going to get started, look at linear regression. The basic idea behind linear regression is that you have two random variables, x and y. And you assume that there is a relationship between them that is a linear relationship. This is a line equation right here. X is the independent variable. Independent variable. Y is called the dependent variable. And you know this. Been doing algebra for however long, you know this about x and y. So we will predict the value of y based on values of x. So our data will indicate to us that there is some kind of linear relationship in our data. Then we will try to estimate what that linear relationship is from the data. Now, we most likely will not get the true linear relationship between the variables. We will only get an estimate of that linear relationship from our data. Just like x bar estimates mu, this line that we develop will be an estimate of the true line that really exists between these variables, x and y. All right, so if you can find that true linear relationship, we call this a regression line. So this is the true linear relationship. So that line, y equals beta naught plus beta sub 1 times x, that's the true linear relationship between x and y. So there is some true linear relationship between those two variables. Call that the regression line. And we know, of course, we already mentioned x is the independent variable. The predictor, it's the thing that we can kind of control, or it's the thing we're saying is independent. Two values of x don't have any relationship to each other. It's just, okay, x has this value sometimes, and then maybe x has this value. What's the corresponding y value? Y is the dependent variable, sometimes called a response variable. It responds to x. For some reason, x changes, y changes just in a linear fashion. So that's called the response variable. Sometimes we call x the control variable, so that's right here, because we have control over the x values. And then you might scatter plot your data, just plot all the data points on the same graph. Call that a scatter plot. And you might see some nice linear relationship here. It looks like the data is linearly increasing. So this would be like linearly increasing data. So as this x, which is husband's age, as that goes up, it looks like wife's age also goes up for the most part. I mean, there's some data points that aren't exactly following that trend, but for the most part, most of the data points in there, we have that upward trend. So if you look at this set of data here, x is the pH of the water and y is the arsenic removed in percent. According to the data that we have here, if we plotted it in a scatter plot, we would see a kind of like a negative relationship. As the pH goes up, the percent removed of arsenic percent removed goes down. So as the pH goes up, the amount of arsenic removed in percent goes down to about 10% or less as the pH approaches 10. So it looks like there's a nice linear relationship there as well. It's just a negative, decreasing. So this would be decreasing linear relationship. So linear means on a straight line. So that's kind of the takeaway. We're not doing any other types of regression here. We're only doing linear regression. There are other types of regression, polynomial regression, all different types of regression. There's a whole class you can take called regression analysis, and it goes over all kind of nonlinear regressions, things like that. Multiple regressions, multilinear regressions, and having multiple input variables, you know, not just x, maybe x1, x2, and those affect y or something like that. So you could have all different types of regression. We're going to focus on simple linear regression, one variable in, one variable out. Okay, so that's kind of our setup. Now, the probabilistic part is that the line is, you know, right here. Here's the line, the true regression line. But the data is not on that line, right? The data deviates from that line. And so we introduce a new random variable called epsilon. So epsilon is the deviation away from the line. So it's the deviation of the data from the line. So it's going to be a random variable that represents the deviation of your data from the line. So you may not be exactly a linear, you may not be exactly a line. You might have like a line, but then you could deviate from that line by a little bit. We call it epsilon, where the expected value of epsilon would be 0. We hope there's no deviation. And the variance of the epsilon is the variance in the data. So let's look at a kind of a different picture, another way to look at this epsilon thing. I don't really care about this stuff right here, so we can kind of skip that. But at each point, at each x value, like x1, we see there's some deviation or variance away from the line. And same thing here at x2. There might be some deviation for the data away from the line. So the data might be anywhere inside this bell curve at each of these x values. So at each x value, the y value is most likely within the bell curve. So that's kind of the takeaway from this picture here, is that the values on that line for y are normally distributed around the line. Okay, so it's not exactly on the line, but there's going to be a normal distribution around that line. So our data points, our y values for each x value are going to be normally distributed around that line. Okay. So we got an example here. It says, suppose we have x, which is the applied stress to a material. We can change that. Then the time to failure is something we don't have control over. It's just going to happen. And assume that from some data we get the following regression line. With the standard deviation was 8, the corresponding function would be this thing right here. Then the y value has a normal distribution. I don't care exactly about these values here, but the important part is that y, the response variable, has a normal distribution deviating from the line with a standard deviation of 8. So this says y has a normal distribution deviating from the line on average by 8 units. And that could be 8 seconds, since our y values are time, maybe seconds or minutes, but 8 units, whatever time is measured in. So here, y is time. So 8 whatever units, seconds, hours, days. Not sure what they're measuring time in here. So probably seconds, that's my guess. Maybe minutes. Hard to say. Depends on what the material is. Okay. So the example, I don't really want to go into the example any more than that. So yeah, let's skip this one too. We'll skip that. Now, how do we get an estimate for the linear relationship? So we want to estimate the parameters beta 0 and beta 1. So that's what we're estimating. We're estimating those parameters for our line. We're estimating the slope and the intercept. So beta 1 is the slope, and beta 0 is the intercept. Okay, now you look at some data here. Got some data. Just going to kind of color over it with green. We've got some data points here. And you might ask yourself, okay, I want to estimate a line that's going to kind of represent this data. Okay, well, I've got 2 lines over here. Got B0 plus B1x, that's this line. And A0 plus A1x, that's this line. So which line better represents the data? Well, definitely the one that's kind of going more along the direction of the data, which is this B0 plus B1x. Well, what's the best line to represent the data? And there's a bunch of ways that we could define that. However, the way we define the best line or the best representation of this data, the best linear relationship of this data, is the line that minimizes the error, actually the square sum of the error. So we will define the best line in terms of this principle of least squares. So this principle of least squares. So this is how we define best line. So we're going to define best line to mean the line that minimizes the sum of the squares of the error from the data to the line. Okay, so here's the line, and here's the data, and here's the line, and then I want to square that difference and add them all together, and I get this function right here. So this is the function that we want to minimize. So we want to minimize f of b0, b1. Okay, so we're going to estimate beta 0 and beta 1 with values beta 0 hat and beta 1 hat. Those are from data. So we will estimate the true linear relationship from our data by constructing a line that goes through our data such that it minimizes the sum of the squares of the errors of the data from the line. Okay. Now, how do you minimize a function? So let me just come over here a little bit just to kind of review a little calculus. So how do we minimize a function? So this is calc 1. How do we minimize a function? Well, what's the minimum of this function, at least as far as we can tell on this interval, AB? Well, it's actually this point right here, right? It's this point right here. So, how do I find that point? If this is f of x, then this point is when f prime of x equals 0, right? When the tangent line has a horizontal slope or no slope at all. And I won't go through it, but also the second derivative at this point is positive, right? Concave up. Although we won't do the second derivative test for this, we will just know that it's a minimum. Let's see. So, but the key takeaway is that this function, take the derivative and evaluate it at this point. We'll call it c. So f prime of c equals 0, and f double prime of c is concave up, positive. We have a minimum of f at c. So that's like the second derivative test from calculus 1. Well, that's great, but we have a multivariable function. So we have a function f of b0, b1, two parameters b0 and b1 that we want to find the values of to minimize a function. So this is actually calc 4 for us, although some of you may not have had it. What you do to minimize this function, you take the gradient of the function and set it equal to the 0 vector. Actually, hopefully this isn't too unfamiliar for anybody, to be honest. I know computer science, you don't take calc 4, but you guys do artificial intelligence, and I know probably a lot of you have taken artificial intelligence, and you talk about gradients in that class, and you talk about gradient descent and all that stuff, so this shouldn't be too intimidating for anybody, hopefully. I mean, even like calc 4 students are like, oh no, gradient again. So it's not a big deal. It's just more derivatives. That's all it really is. So hang in there. Not going to spend a lot of time doing this derivation, but I did want to spend a little time talking about, how do we minimize this function? So what's our function? F of b0, b1? Well, that's going to be the summation I equals 1 to n of yi minus parentheses b0 plus b1x, b1x I square. So that's our function. And what's the gradient? Well, the gradient of the function is something we call a vector, and it's the partial derivative of f with respect to the first variable. In this case, the variable is b0, and then partial f with respect to the second variable called b1. So that's the gradient of this function. So what we need to do is calculate partial f, partial b0, and partial f, partial b1. Well, partial f, partial b0 means I need to take the derivative with respect to b0. So taking the derivative with respect to b0. See, I can move the derivative inside the summation. So that means I can say I equals 1 to n 2 times yi minus b0 plus b1 xi times the derivative with respect to b0 of the inside, which is just -1. And set that equal to 0, because this is supposed to be equal to the 0 vector, which is the vector 0, 0. And the same thing here, partial f, partial b1 is going to be the summation I equals 1 to n 2 times yi minus parentheses b0 plus b1 xi times derivative of the inside with respect to b1, you just get xi here. And then set that equal to 0. Let's see, there's a negative there, so I don't need to forget that negative, because that would technically be distributed to the b1 xi as well, so that's actually negative xi when I do that chain rule differentiation. And now what we can do is we can divide both sides by 2, distribute that negative 1, and we could say that this is the summation I equals 1 to n of b0 plus b1 xi minus yi equals 0. Same thing down here, divide by 2, distribute the negative xi, get the summation I equals 1 to n. We'll call it b0 xi plus b1 xi squared minus xi yi equals 0. And now we're just going to rearrange the two summations. So now if we just rearrange the two series, or the two summations, we'll get something of the form, let's see, b0 is just a constant, so the summation from 1 to n of b0 is just n times b0 plus b1 times the summation I equals 1 to n xi equals the summation I equals 1 to n yi. And then down here we get the b0 times the summation I equals 1 to n xi plus b1 times the summation I equals 1 to n xi squared equals summation I equals 1 to n xi yi. And now we have a system of equations, two unknowns. So this is a 2 by 2 system of equations. The variables, don't forget the variables, are b0 and b1. So b0 and b1. The coefficients are the series. So the coefficients are the sums. So you pick your favorite method to solve the 2 by 2 system of equations. You could do substitution, so solve with substitution. So you pick your favorite method, and it turns out that b1 ends up being summation I equals 1 to n xi minus x bar times yi minus y bar, because you'll be dividing by n a few times, so just be careful doing the algebra, over the summation I equals 1 to n xi minus x bar squared. And some people call that sxy over sxx. And b0 is summation I equals 1 to n yi minus b1 summation I equals 1 to n xi all over n, which could be written as y bar minus b1 x bar. So that is the derivation of the two parameters, or the b0 and b1, that minimize the function. So these two values of b0 and b1. So this is the values of b0 and b1 that minimize the square sum. So these are the minimizing values of b0 and b1 for f of b0, b1. And we give them a special name. We call them beta 0 hat and beta 1 hat. So we call it beta 1 hat. And then here we call it beta 0 hat. So they're just estimates of the true values beta 0, beta 1 for the underlying relationship. But they came from our data, so we give them a hat, basically. So we can get back to the slides over here, and that's where we get those values. So we'll pause for a second, see if there are any questions. So there's actually an easier formula for these two, right? Because these beta 1 hat, beta 0 hat, these two right here are not very friendly. Well, beta 0 hat's not too bad once you have beta 1 hat, but so the better formula to remember is probably this one right here. And I'd probably remember these two. So remember these two. So you use these two formulas for calculation purposes. And what does that do? That gives you an estimate of the line that models the true relationship between the two random variables x and y based on your data. Just like x bar estimates mu for a population based on some data. So that's the same thing going on here, except we're estimating a linear relationship. So this line is the line that is minimizing the sum of the squares of the errors of the data from the line. So any questions so far? All right, so we got an example to do all this stuff ourselves. Go through and calculate all of this stuff. This example says cetane number is a critical property that specifies the ignition's quality of fuel in diesel engines. Determining cetane number for biodiesel fuel is expensive. Iodine value is the amount of iodine necessary to saturate 100 milligrams of fuel, less expensive to determine. We have data from 14 samples of biodiesel fuel. Y is cetane number and X is iodine value. Let's develop the least squares line, the linear regression line, or the estimate of the linear regression line. So what we're going to do, we need to add up all the x values. So from I equals 1, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think they told us, yeah, 14. So n equals 14. So from 1 to 14, we sum up all the x values. And I've done that to get 1307.5. And then sum up all the y values, I equals 1 to n. And we get 779.2. And then sum up I equals 1 to n, all the xi values squared, So square the x values and then sum them, and we get 128,913. Do the same for y, summation, I equals 1 to n. Take the y values, square them, and then add them together. Get 43,745. And then summation, I equals 1 to n xi times yi. And we get 71,374. And now we just need to plug and chug in our formulas. So this is going to be beta 1 hat. It's going to be 71,374 minus 1 over 14 times 1307.5 times 779.2 all over sum of xi squared, which is 128,913 minus 1 over 14 times 1307.5 squared. And I get that value is negative 0.209. And then beta 0 hat is, let's get the calculation. You just go up there, calculate y bar. That's the sum of y over n minus beta 1 times x, which is negative 0.2094 times the summation of x, which is, or summation of x over 14, which would be 1307.5 over 14. So let's do that. That's going to be 1 over 14 times 779.2 minus 1 over 14 times 1307.5 times negative 0.2094. And we get beta 0 hat is 75.21. So we got our linear regression estimates, beta 0 and beta 1. Just double check. Yes, 75.2136. Let's just say 21. So that is our least squares regression line. Okay, that's our least squares regression line. Our slope, negative 0.2094. Our intercept, 75.21. So we have a negative relationship because the slope is negative. So the slope is negative, meaning there's a downward trend. As x gets bigger, y is going to get smaller. So this is called the least squares regression line because it's created using the parameters that we derived using the least squares method. So this is called the least squares regression line. And now we could use that to estimate any other x value that we want with a certain amount of certainty, within one standard deviation, or you could figure out the probabilities and all that stuff now. But yeah, let's use x equals 100 and estimate the cetane level, right? Y is the cetane level. So estimate the cetane level at x equals 100, which is the iodine value. So at an iodine value of 100, what is the corresponding cetane level? Well, probably 54.27. So about like right there. So we estimate the value of cetane from the iodine level using the least squares regression line. Cool. Note, we are doing interpolation, not extrapolation. We're only going to estimate values within our range, because within our range, let's say in this case it was like x equals 60 to x equals 135 or whatever, we can see there is a linear relationship inside that range, or at least we assume there's some sort of linear relationship. Thanks. We can see that there's a linear relationship between the x and the y values here, but we don't know outside of this interval if it's going to be linear or nonlinear. We have no idea, so we can't really extrapolate, but we can interpolate. We can say, okay, inside these bounds of these x values, I see a linear relationship. So I'm going to use this least squares linear regression line to estimate that linear relationship and plug in x values to that line to get the corresponding y value. So we are not doing extrapolations. No extrapolations with linear regression. Take a break, take a second, see if anybody has any questions. I know I got to slow down. You guys are always telling me to slow down, so I'm going to slow down, make sure nobody has any questions. Okay, sweet. Well, how can we estimate the standard deviation in the data, right? How far are we deviating away from the line? Well, we could use our estimate line, our least squares line, to estimate how far we're deviating away from the line in general. So the fitted or predicted values, y1 to y1 hat to y2 hat, yn hat, are obtained from the regression line. So that would be like, on the line, x1 here, y1 hat would be right there on the line. So that's y1 hat. And maybe x2 is right here. y2 hat would be right here on the line. Whereas, y2 itself may be up here. So this may be the actual y2, and this may be like the y1. They're not exactly on the line. So that's what those hat values are. What we're going to do is look at the error between those two, the values on the hat, or values on the line, which are the hats, versus the values of the actual data, and find out what we call the residual. So this difference is called the residual. And that was more or less what we were trying to minimize. Do we have class Friday? Good question. Let me see how far we get today, and we'll talk about that maybe a little bit later. So let's see how far we get today. This is called the residual. It's the difference between the data and the least squares line. So it's the difference between the observed, or the data, and the fitted values, or the least square predicted values. Values predicted by the least squares line. Then we can use the residuals to estimate the standard deviation. Now, I don't want to confuse you, because the last time we went over a bunch of things like SST and SSTR and MSTR and all that mess. But we have another thing called square sum of errors, which is the summation from I equals 1 to n of the square of the errors all added together. So this is the sum of squares, residual sum of squares. So you're taking the difference, the residual, so this is the residual, you're squaring it, and then adding them all together. And you could do some algebra to manipulate it and change it and make it look like that, but the important part is this error, you're squaring it, deviating away from your predicted value. So this is the square of deviations from estimated value. That reminds me a lot of sample variance. When we deviated away from x bar and we took all the x values and looked at where they were deviation away from x bar. That was the sample variance for your data. Well, now the y values are deviating from the line, so how much? Well, we square it, add them together, divide by, in this case, n minus 2, and this is an estimate for the variance in your data, your y values. So this is like the variance. And the y data from least squares line. So this is an estimate for the actual variance in y. So this is an estimate for the actual variance in y. Why do we need to estimate the variance or the standard deviation? Well, that tells us whether or not we have a good fit. If the variance is really small, we have a really good fit. If the variance is really large, not such a good fit. So to find out how good the line is fit, this would have small variance. So this would have a small variance. More variance. And this would have large variance. So at the last one, I'm not even really sure which way the line should go. You know, would the line be that or this? I'm not sure which is the best line. Really hard to say. So basically, can I explain the variability of y on the basis of x? Well, in the first one, yes. In the second one, still yes. The third one, probably not. Not going to be able to find some kind of linear relationship there. So the SSE is how much variation in y is left unexplained by the line. The model, that just means the line. Y equals beta 0 hat plus beta 1 hat x. The model is the equation. Cool. So let's calculate this S² value for that cetane iodine. Okay, well, we have to plug in all the x values to our line. So we plug all the xi's into y, which is beta 0 hat plus beta 1 hat times x to get all these y hat values. Then we compute SSE, the residuals squared and added together. And then we divide this number by n minus 2. And we get the sample variance is 6.57. So the sample standard deviation is 2.56. Questions. Again, I'll slow down, pause, see if anybody's got any questions, let people catch up. Really trying to be super conscious. Make sure I'm not flying through. Okay, last thing before we wrap up today, we're going to develop something else called the coefficient of determination that really tells us if our variance is small or large, more or less. So we're going to develop a coefficient of determination by comparing our variance, SSE more or less, to the variance of the worst possible prediction that we could come up with, which would just be the line y equals y bar. So this is the worst possible predicting line. So the worst possible prediction line. That basically says take all of your y values, get the average, and that's what your value is going to be for any x value. All right, that's the worst possible predictor if you have some sort of linear regression or some sort of linear relationship, positive or negative. So we're going to say, okay, let's compare our variance, sample variance, to the variance of the worst possible line, which would just be y equals y bar. So what we do is we compute the square sum for y bar, the residuals from y bar. That's basically what this is, residuals compared to y bar. Add them together. We can do some algebra. So just algebra to rewrite. So this is the worst possible prediction, and that's more or less its variance. We have to divide by n minus 2. But what we're going to do is we're going to take the ratio of our square sum. So this is our variance. This is the worst possible variance. Worst possible variance. Notice if I were to divide by n minus 2 in each case, they would cancel out. So if our variance is really close to the worst possible variance, then this ratio is really close to 1, meaning this difference, 1 minus 1, is basically 0. So if, so let me just note here that if SSE is close to SST, that means 1 minus SSE over SST is close to 0. Well, if SSE is close to SST, that means we have a bad fit because we know y bar, which is coming from, or what we use for SST, then that is the worst possible approximation, and we're close to that worst possible approximation. We're not much better than just using y bar if SSE is close to SST. On the other hand, if SSE is much smaller than SST, 1 minus SSE over SST is about 1. So that's why we say right here that r squared close to 1 is a good fit and r squared close to 0 is a bad fit. And this r squared thing is called the coefficient of determination. So coefficient of determination, r squared. And we could calculate the r squared value for our example. We get this value from our calculation. We go ahead and calculate SST. And that's 377.174. R squared, 0.791. So pretty good fit. Not a great fit, but pretty good. So this is a pretty decent fit. So pretty decent fit. If you get closer to 0.9, that's really good. But 0.79 is pretty good too. 0.8 basically. So what this means, 79% of the variability in cetane number can be explained by the linear regression fit to iodine value. So that's what this R-squared value tells you. We're not going to get into this today. We'll do it next time. Start talking about the hypothesis testing and stuff. This is going to be testing whether or not beta 0 or beta 1 is a particular value. So we want to estimate, we want to say, okay, is it likely that beta 0 or beta 1 has any particular value? Well, we have some data. We calculate our estimate, compare it to what it would be if it were the proposed value in the hypothesis, and get a p-value and fail to reject or reject the null. So we're going to do some hypothesis testing starting next time. But we'll stop here for today. It looks like we're more than halfway through, so yeah, I think maybe let's not have class on Friday. So Friday we'll take the day off. Monday we'll be back. We'll finish up chapter 12 probably pretty quickly, about the same amount of time or less, maybe an hour. Maybe a little less than an hour, about 45 minutes maybe. Kind of go through some review on Wednesday. First part of the exam on Friday. Final chapters 8, 9, 10, and 12 on Monday. So that is the plan for the rest of the quarter. Any questions?